All right, so in the middle of the back of the first page, we're going to be solving logarithmic equations when there's multiple logarithms. And so we are going to have to use those properties we just talked about. If there's multiple logarithms on one side of the equation, we're either going to use multiplication or we're going to use division to bring it together to one logarithm. And then we're going to decide which form it is. So if we bring those logarithms together and you end up with log equals a number, we're going to do it just like we did the last class. You may or may not remember those examples right there, example 2, where you write it in exponential form. If it's form 2, where you have log equals a log, then what you can do is easier. You can just drop off the logs and you say that those arguments are equal to each other and you just solve it algebraically. It's pretty simple. Now, one thing to pay attention to is that we need to check for extraneous solutions. And so you can do everything you're supposed to do, but then when you plug the answer back in, you get something that's undefined or something you can't have, mainly dealing with the arguments. So the arguments have to be greater than 0. So you can't have a negative, you can't have 0 as an argument. So that's where you might get an answer that when you plug back in, it just doesn't work. And it's nothing you did wrong, it's just how the problem is designed. All right, so let's look at example 3. So before we start solving it, let's talk about the values that of x that are possible, that are defined. And so if we look at this first argument, we know that x plus 4 has to be greater than 0. So what does x have to be greater than? Negative 4. All right, and then if we look at the other argument, x minus 5, no, I don't know what I'm saying. 5x minus 2 has to be greater than 0, so that means x has to be greater than 2 fifths. So let me ask you a question. If x is greater than 2 fifths, is it automatically greater than negative 4? Is anything greater than 2 fifths automatically greater than negative 4? Yes. That sounds like a trick question, but it wasn't. So we don't really have to worry about that one. We just need to make sure when we do our answers that they're all the answers that we get for this particular problem have to be greater than 2 fifths. And if they're not, we just mark them out and say they're extraneous solution. All right, so let's keep going. That's going to get easier as we go through. So right now that felt kind of weird, but we're going to do it on each problem and you're going to be fine. All right, so these two logarithms are separated by addition and we need to bring them together. What are we going to use to bring them together? Multiplication or division? Multiplication. So we're going to multiply 3 by x and multiply 3 by 4. All right, and then the other side, there's just one logarithm, so I'm just going to bring it down like it looks. All right, and then this is like the new type that we're dealing with, form 2, where we have log equals a log. And when you have log equals a log, they have the same base. You just set the arguments equal. Because if this log equals this log, then the 3x minus 12 has to equal the 5x minus 2. Or 3x plus 12 has to equal 5x minus 2. And then it's a super simple equation to solve. All right, so originally we get that x is 7, but on all of these we have to make sure that that can be an answer. So is 7 greater than 2 fifths? Yes, so it is a solution. It checks out. All right, and that's pretty much it. That's how you solve these problems. All right, let's look at another one. So B. So I'm looking at my arguments. Now the one that's 7, we don't worry about. Just like on this one, I didn't even worry about 3 because there was no x there. So I really only have to be concerned about one of these. Which one do you think it is? The one with addition or the one with subtraction? We only have to be concerned about the one with subtraction. So we can still do like what we did on the last one, but the one with addition is just, it's not going to be necessary for us. All right, so for you to have an answer that's an actual answer on this problem, your x needs to be greater than 5/3. All right, and these are separated by subtraction, so we're going to bring them together using division. So the argument that's positive in the front is going to go in the numerator, and then the argument that's negative is going to go in the denominator. And this is another situation where we have a log equals a log, so we can just drop off the logs and set those arguments equal to each other and solve. So just like always, when we're solving an equation and there's something in the denominator that you don't want there, you can just multiply by it. All right, and then again, it's just a couple of steps. All right, so we originally get 36 over 20, which will both reduce by 4. And so that's 9/5. Maybe 9/5 is the answer. This one's kind of tough. So do you guys know which is bigger, 5/3 or 9/5? 9/5 is bigger. So 9/5 is 1.8. 5/3 is about 1.7 or 1 2/3. Now, if this was a non-calculator question, you might actually have to do that division by hand or write them with the same base. Both things I think you're capable of doing. So you would take 5 and divide it by 3. And then here, it would keep going, but here you would take 9 and divide it by 5. And then you could tell which one's bigger. Okay, let's keep going. So on C, we're going to go ahead and look at the argument that if we have a plus and a minus, we're just going to look at the plus, and we know that all of our answers for this problem have to be greater than -2. Right, and then I have 2 logarithms separated by addition, so I'm going to bring them together using multiplication. Separated by addition, we're going to bring them together using multiplication. So I'm going to distribute that x and distribute the 2. All right, and then it's another logarithmic equation where it's log equals a log. So I'm just going to drop off the logs. And then I'm going to solve this for x. Now, it's been a little while since we've solved quadratic equations. I would highly recommend that you just try to solve by factoring. Most of the time, these are designed so you can solve by factoring. They're not going to be, probably won't be any that are too weird. So we would get everything on one side and then factor. Now, I'm just going to tell you, most of the time, not all of the time, but most of the time on logarithmic equations, if you get 2 answers, one of them is the extraneous answer. Logarithmic graphs look like this. And if we're trying to find where 2 logarithmic graphs are equal, most of the time they're only going to cross at one place. Now, it's possible they don't cross at all. So sometimes we're going to get some of these with no solution. It is possible to have two solutions. So don't think that is always one of them isn't going to work, but it's more than likely one of them is not going to work. So which one it doesn't work on this one? -4. So -4 was extraneous. 5 is the only solution. All right, how y'all feeling about this? It's okay? There's a lot to remember, especially after being out of school for an extended period of time. Okay, let's look at D. So we're going to bring these together using division. So the natural log of x divided by 3 is equal to 2. And once we do that, this is very similar to what we did on example 2 up here. So once we have just log equals a number, we're just going to write it in exponential form. So what is the base of natural log? E. So this is e squared is equal to x over 3. And then to solve that for x, we would just multiply by 3. And there was something I forgot to do. I didn't talk about the domain. So if I'm looking at my arguments on this one, x just has to be greater than 0. Is 3e squared definitely greater than 0? Yeah. So e is like 2.8 something. And so when you square that, you're definitely going to get positive. So we're good. All right, now we do have a shortened class period today, so I'm not going to do all of these examples. I'm going to get started on example 4, and then we're going to skip all the way down to example 7, just so you have a little bit of time to work. All right, so on the reason I want to do example 4a is because of this 3 in the front. So right now, I cannot bring these logarithms together. What do you guys think I need to do with that 3? It's been a little while. A week ago, you would have been able to tell me pretty quick. Move it to exponent. All right, so when I bring this together, it's going to be log base 4 of x over 8, because 2 to the third is 8. All right. And then we would just drop off the logs. We're not going to solve this. It's okay. You actually get an answer that doesn't work when you plug it back in. It's not in the domain. All right, and then for this one, so I have a log minus 2 and I have a log. I can't really bring these together because 2 doesn't have a log. So any ideas on what I can do? There's 2 things I can do. One of them is a little easier, I think. What I would probably do is move the 2 over by itself and move the logarithm over here. So you would have log of x minus log of x minus 7 equals 2. The other thing you could do is write 2 as a log. What's the base of just log? 10. So I wouldn't recommend that you do this, but you could write 2 as log base 10 of 100, and then you could bring them together using division. Either way, I think this way is a little bit easier. All right, we're not going to finish it, but we're going to get started. Keep going just a little bit. All right, and then like you guys said, no base means base 10, and you would write this in exponential form. And you get some ugly fraction. You get 700 over 99. It's an acceptable answer. It is in the domain. It's just kind of weird. And I want to get done with example 7. Okay, so the last type we're going to solve are going to be exponential functions. And we did exponential functions before, and they were when there was just one exponential expression. These are going to have 2. So when there's 2 exponential expressions, what you're going to do is write these with the same base. So we can often solve by finding common bases. Now, example A already has a common base. So if 2 raised to this power is equal to 2 raised to this power, What that means is those powers just have to be equal. Right, and then again, it's just a simple, whoops, I was trying to do too much at one time. Now, there are no limitations on exponents. Exponents can be positive, negative, zero, anything. So we shouldn't get extraneous solutions on these problems. All right, so starting on B, they're getting a little more challenging. So what we need to do is write both sides of the equation with the same base. So what base do you guys think it needs to be? 2. So 8 is 2 to the third power. So in the place of 8, I'm just going to replace it with 2 to the third. And then the other side already has a base of 2, so we just leave it. All right, and then this goes back to one of the properties on the front. When you have a power raised to a power, you multiply those powers together. Now, some of these things I think you can do in more than one step, but I don't want you to get confused on your notes. All right, so once they have the same base, you can just set the exponents equal and solve for x. All right, and then for C, so look at C. We should, if we can solve this problem this way, we should be able to write 9 and 27 with the same base. What base? 3, yeah. So 9 is 3 squared. So in the place of 9, we'll write it as 3 squared. 27 is 3 cubed. And then I would multiply those together. So if you want to multiply those together and drop off the bases at the same time, you can. That's fine. If not, you just go ahead and distribute those numbers. Okay, and then we'll set the exponents equal. And we get 6. All right, so we have one more. So you guys look at that. 1/2 and 4, we want to write with the same base. Two. Very good. So the base is 2. So 1/2 is 2 to the negative 1, like you said. And 4 is 2 to the second. Okay. And then I'm going to distribute that. You can distribute and set them equal at the same time if you want to. All right, and then we're just going to get that x is negative 1. And so I can put negative 1 here, put negative 1 here, and I'm going to get the same answer, which would be 1/4 equals 1/4. Yes, sir.
When you're solving exponential, is there any way for them to be extraneous?
I don't think so. Not that I can think of, because there are no limitations on exponents. It can be anything. I can't think of a time when it would be extraneous. All right, any other questions? Okay.